You're set. All right. Welcome to class again. Who's happy? All right. I was, things were fine for me this morning, but it just felt like one of them bleh days. Wasn't zesty. I'm feeling better now. All right. I have physics. Okay. The chair of our department asked us to read this. As of Tuesday, yesterday, all faculty are required to inform students that are not officially registered that they may no longer attend class. Anybody not registered? Well, good. Doesn't apply to us. But for your other classes, in case you're curious, it's required by university policy, and to receive proper remuneration for the teaching they're doing. You can't do that. You can't attend if you're not registered. You can register for credit, no credit, and do that auditing thing. You can look into those, but I guess you're not allowed to just sit in for the sitting in sake. You must be registered one way or another. And number 2. How many got my email about clickers? Okay, good. I sent it to the whole class, to your official ID number email, so please go read that. But the gist is this. Clickers are still good. I'm still using them. I still have everybody's response, that at least it's asked me, to check. My problem has been hooking up your device ID number with you so that you get credit. I can see device numbers, but it didn't always match up with you. So I still have all the responses, and I can fix this. It had to do with their new software and new integration with Canvas. To help us do that, I did not realize, they didn't tell me, these, I told you to register your device ID number, correct? And most of you, I assume, have all done that have a clicker. Your mobile device, your ResponseWare device, you have to register that ID number as well that they give to you at the same link that I told people to register their clickers. It's in the syllabus, the WebReg, turningtechnologies.com or something. It's in the syllabus. So look under clicker where it says register your clicker device ID number here. You have to register your ResponseWare ID number also. So if you are using ResponseWare and have not done that, please do so. When you sign up for an account and purchase the license, they send you an ID number for your mobile device through an email. That's the number you'll register then. Hopefully that'll take care of some. And with clickers, they told me that if you have ID entered into here, information into your clicker, that can mess the integrations up also. I explained this in the email, but those of you that have a clicker, if you'd like push a button to turn it on, you'll get a little tools button. A tool icon. This is the NXT model, and it's in the upper right-hand corner. I see a little wrench. If you select that wrench, then you're in a menu. Mine, the first thing that pops up is Find Channels. If you right arrow, you can scroll through the menu options. Note to leader? No. Device info? No. Contrast? No. Your ID. Yeah, that's the one we want under the Tools setting. I'm going to select that by hitting the big center silver button. And it says Your ID with a blinking cursor. Mine's blank. That's how yours needs to be. If you have any info in there, you need to backspace and clear it out. And then hit the enter button to save that. So you shouldn't have anything under Your ID in your clicker. And maybe I'll stop getting some funky names on the integration. But again, it's in the email. Do that. Maybe by next class there won't be anybody left. I can keep looking. Still doesn't matter. We can still use these. I still get your responses. You'll still get credit once we hook you up. Does that make sense? All right, I'm going to start with some clicker questions. So go ahead and pull them out. There's under that menu option under your ID, there should be nothing. Just a blinking cursor. No name, no nothing. All right, let's quiz you. All right, in the bottom right-hand corner, channel 44, and the session ID number. Over there in the bottom right. Someone asked about reserving a session ID number. I figured out how to do that and then decided we're not doing that. Sorry. And the reason why is because the administration has had bad experiences where, if you hadn't thought of this yet, you could stay home, log into the same ID session number because you already know what it is, and still enter responses and get credit without being here. So we will have a different session ID number every class. Sorry. There it is. All right, I wanted to ask... I don't care if I went too fast and you saw the answer. Anyway, I want to ask this one. All right, polling open now. I won't lie, I'm hoping this one's easier, but I want to find out. See how you're understanding. Yes? Oh, so you hadn't done it yet. Okay. 855-269. The session ID number for ResponseWare is 855-269. All right, I'll give you, it looks like most responses are in. 10 seconds to get your answer in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and... All right, the majority answered D, mass. The next biggest was A. The correct answer is mass. Why would it not be initial speed? Why would that not affect acceleration? I mean, if you're starting out faster, would that make you go faster? What does faster have to do with acceleration? Good. Acceleration is a change in velocity. So yeah, you might be going faster, but that's velocity. But the rate at which you're changing your velocity, how fast you're going, is acceleration. And so whether you started going fast or slow, the acceleration is just that change. It doesn't depend on the initial speed, but it does on the mass, Newton's second law. Did you have a question, Brian? Yeah, difference between a child and an adult opening the door. And that's exactly right. The more massive something is, the more inertia it has, and the more it wants to resist that change in motion. Thus, it won't accelerate as greatly. All right, I want to ask this one. Go. Sack of potatoes falling through the air. I did make all my tie-dye. Well, I have one out of, 30 that I didn't make. But my friend did. Yeah, I made this one. How are we doing? I'll stall. You can still answer. Polling's still open. I had a job with the Little Shop of Physics as an outreach program at Colorado State University when I worked there. And our tour shirts were tie-dye. We'd make a different one every year. And that's why it says Little Shop of Physics. And this one probably has the schools we visited. But after the work shirts were made, we could tie-dye anything we wanted. So, yeah, I have lots of tie-dye. All right, get your polling in. 3, 2, 1, and... Oh, good. That makes me happy. 92% of you got the correct answer, all of the above. If something's falling, it's moving down. So, yeah, the air drag is up. But I wanted to make sure you guys realize that as it moves faster and faster, the air against it's moving faster and faster, and that will increase the drag. That was C. B about the area. Yeah, something's bigger. It's going to hit more air, so that'll increase air drag. Good, good, good. Any questions? I wanted, no, this one. Polling open now. See, I think this is fun. This way you all participate instead of the same 3 people only answering. So. Friendly reminder, I'm not counting wrong if you get the wrong answers. I hope you are answering honestly so you can find out. But sorry, I prefer you answer period than necessarily get it right. Most people are in, so 5, 4, 3, 2, 1, and I am curious though. There's 49 responses. I know 70 people are registered. So those of you that aren't participating, it's by choice. You're aware of what you're doing. You just decide not to buy a clicker, or maybe everybody's just not attending, and you guys are all doing fine. Okay, just want to make sure. This one split a little more. We got 55% thought B, but 30% thought A. So this, what I like doing, talk to your neighbor. I'll give you a minute to discuss to your neighbor and explain why you thought. It seems that the majority think it's A or B. Convince your neighbor of your reasoning. And I'm going to open up the polling. You can re-vote. I've learned that I can tell students one thing, but if one of your peers tell you the exact same thing, you tend to believe them more. So.
Are we talking about from the beginning of the fall?
Doesn't matter.
Doesn't matter.
For any given second, yeah. For each of those seconds. Whether it's this second, this second, this second.
No, because for the falls, start with the zero.
Doesn't matter.
The maximum speed until
It'd be the same answer no matter what second you're looking at. What segment.
it's going to be the same.
Yeah. It doesn't matter which part of the fall you want to look at.
Okay.
All right, go ahead and get your new response in, whether it's the same response or not. 10, 9, 8, 7, 6, 5, better hurry up, 4, 3, 2, you guys don't want to vote again? 1. All right. Sweet, now we're split 50-50. All right. The correct answer is A. So let's discuss this one some more. See, now I know you guys have thought about it more, so you'll remember it, I hope. During each second of free fall, first of all, that tells me free fall. I don't have to worry about air resistance. This is just when it's just under the influence of gravity. The speed of an object increases by the same amount. The speed. Let me ask you this, because I've done it before. What's the acceleration of the object? 9.8 meters per second squared. Good. I'm going to round to 10 for convenience. So during the first second, how far does it fall? No. What speed does it get up to after 1 second? 10 meters per second, because it accelerated 10 meters per second a second. So how much does it, what speed does it get up to after the second second? 20, 30, 40. So the change for each second is what? Same, 10 meters per second. Does that make sense?
So the only difference is because it doesn't have any air resistance.
If there was air resistance, what would happen? It would slow down with each second as the air drag increased. Until what happens? It hits terminal velocity, in which case the velocity is doing what? At terminal velocity, the velocity, not zero, you're still moving. You're in equilibrium, so it stays the same at some terminal velocity. And so you fall at a constant rate the rest of the way. You go ahead first. Yeah.
What was that thing when you dropped the ball and it was just faster down here and as opposed to right here and you were explaining it? Wouldn't that be because
it is faster down here because with each second it picks up speed. But for each second of fall, it picks up the same amount each second. So it does end up going faster and faster, but by the same amount each second. 10 meters per second. Another 10 meters per second, 20. Another 10, 30.
No, I was going to say that's exactly why I was confused about these. So.
Well, good. I'm glad I asked this question then. You guys feel better? I think there was one more I was interested in. Yeah, this one. Polling open now. This one requires a little more thought, but I think you're ready for it now. So. My clue to you now is, which one's going to feel more air drag? Why? That would differentiate. Or, if you prefer to think of terminal velocity, do they both reach the same terminal velocity or not? Looks like most of you are in, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You guys like A and C. The majority is on A. It is the heavier one. Someone that chose that, would you be willing to explain your reasoning? Red shirt.
Kind of like the same thing with like a feather. Like the less mass you have, like the more the air
So he's saying things that are lighter, like that feather, has less mass, so less inertia, less resistance to change in motion and acceleration. So it's going to be affected more and slowed down more, thus hit the ground later. Did I cap that up well for you? Who wants to add to that? Or did you come at it from a different thinking? Oh, well, him first.
The lead one has more mass. They're both the same shape, so air resistance really has no factor.
They're the same shape, so that they would have the same drag just by area. Good.
It has no factor in this problem. You can't say, well, it's going to, surface area doesn't affect proportion.
Yeah, area doesn't affect. Good. Let's see what Brian adds.
In the book, I was reading about the Galileo dropping two balls, one that was heavier than the other. And then, you know, they hit at the same time, though. But how does that work?
So the heavy and lighter ball hit at the same time. In most things that we do with normal objects, air resistance isn't much of a factor. But when we drop, so like when I dropped the book and a crumpled up piece of paper, do you remember that? They hit at the same time. If the paper was open or I used a feather, that made it way more dramatic and obvious that air resistance slowed it down. If I were to take the book and the crumpled up piece of paper and drop them out of an airplane like this, so they had a long time to fall, do you think they'd hit the ground at the same time? No, they would not. Because this one's lighter, it does have less resistance to change in motion, so it does slow down more. Who's going to have the greater terminal velocity? The book, the bigger mass. And so it'll be moving faster. And it'll actually have more air drag on him because he's going faster. But the balance is going to arrive at terminal velocity at a higher velocity for the heavy object than the lighter object. Thus, he's going to get to the ground faster because he's going at a higher terminal velocity. So the heavier person will still hit. I think there's a lot of good physics we can bring together in this problem. Does that make sense?
So if it's dropped from a higher point, then the object that has more mass will fall first. But if it's not as far up, then it'll hit about.
Well, technically, they still don't fall. But the higher up you drop it from, the more time air resistance has to act and makes it more conspicuous. So just like that example, the book and crumpled up paper in class from here hit at the same time. But yeah, if I moved it just to the ceiling, I bet you'd see a little difference.
Or skydiving? So if it was me and another person that's lighter than me diving off a plane at the same time, that air resistance at first would be there, but I would reach terminal velocity first. Or would the other person first?
Who would reach terminal velocity first, the heavier or lighter? I have to think about that one. I know once you guys reach them, yours will be faster.
Well, it depends on how he spreads out.
Assuming they're the same area then, we'll keep it simple, but you're right. I'll be honest, I don't know off the top of my head. I can think about it though and get back to you. I don't want to tell you wrong and have you be confused. Yeah?
If you have a heavier object and a lighter object, do they still accelerate at the same speed even though the lighter object
Do they accelerate at the same speed?
has less terminal?
Initially, what's their acceleration? You know this. Right. As air resistance creeps in, what happens to both of their accelerations? It slows down. The net acceleration slows down because you have gravity still pulling down at 9.8, but air resistance is pushing up. So they both slow down their acceleration. And if they both hit terminal velocity, what's their acceleration now? Zero, because their velocity is not changing. Does that help?
Yeah, so the heavier object just doesn't slow down as much as the lighter object.
Correct. The heavier object will not slow down as much because his terminal or her terminal velocity will be faster. Yeah, so bottom line, it's not a big difference between him and you if you were to jump out. But there is a difference, and you see my point. An elephant and a mouse. The elephant would clearly hit the ground first. Now, they have different size differences, and that would come into play, but I don't think it's enough to matter in that case.
Well, so from the mentality of greater mass, greater inertia, greater everything else. So Galileo was wrong in his tower drop experiment.
Well, what he, yes and no. He was neglecting air resistance. Neglecting that, he's right. He learned Newton's second law, which we've learned, and it's true. If you then account, though, for air resistance and air drag, all the stuff we've just been discussing still fits Newton's laws. We're not invalidating them. But his law was ignoring air resistance. So in a way, he was fortunate. And there's actually some debate whether he actually went up to the tower and dropped them in real life or not. We don't really know that. People like to say that, but there's been talk that maybe he never even went up and did it. But what he did do was roll things down inclines. And they're going slow enough, and the air resistance was negligible there, and he realized these laws that I've been teaching you. But the key is, in real life, things you have to deal with, there are often other forces at play. Air resistance, resistance of a table, and those affect the motion as well. So remember, Newton's first law is things will stay in motion as long as no other force acts on them, right? It's just quite often we see another force acting on it. He was, I think, clever enough to dissociate those two to make that law clear for us. But we get muddied down because in real life we always see these forces confusing us. I know when I throw that it's going to go and stop. We don't see the going off for everything. Good discussion. Thank you. You can put your clickers away. Newton's third law. Friendly reminders. I'm starting chapter 5 right now. We'll finish it Friday and have time for some review. So if you guys have questions about anything up to this point, bring them Friday, because your first exam is Monday on everything. It's I made it up. This one will be 30 questions. They're multiple choice, very similar to the ones I asked you in class and that you've seen on homework. They'll all be multiple choice. I'm going to use the bubble sheets so you can fill them in that way. In the past, practically everybody feels like they have plenty of time to complete it, unless you feel like, oh no, most people are done early. I will allow you to use a calculator, that's fine, I don't mind. And I will allow you to even have a cheat sheet. One side of one piece of normal paper, you can write what you want, because some people stress, oh, I can't remember the equations. Write them down, it's fine with me, because I'm testing you about how you use them anyway. So, you still have a question?
Well, mine was if we could use them.
One side of one piece of normal 8.5 by 11 paper, knock your socks off. When we are testing, I will want you not sitting by somebody else, so you'll space out and you'll just have your sheet. I don't want to see books and things around, but I'll remind you of all this. There's another. Can I post the question, the clicker question for online? No. However, these are being videoed, so friendly reminder, you guys can go back and watch all these. Study guide? No. The book is great. I don't know. I hope you guys have been following it and see that I am pretty darn close with this. It explains it like I do, or I explain it like it does. The example questions in here are like the ones I asked. The ones at the end of the chapter sum it up. And you do have the videos to review, so no, I wasn't going to specifically make up a separate outline to explain all this. During class, I'm going to finish up whatever I didn't feel like I covered sufficiently for Newton's third law, and then review everything based on your questions or I feel is important. Pretty much what I emphasize in class is I feel is important. Yes? And this homework, instead of being due Sunday night, like has been typical, since the test is the next day, I wanted to make sure you guys finished it a little earlier and had a chance to review the correct answers. Thus, this homework is due Friday night. This homework is due Friday night. And another friendly reminder, I announced last time our teaching assistant, our TA, is posted. I made an announcement in WebAssign and updated the syllabus. She is offered to have office hours Monday through Friday from 2 to 4 in her office, which I don't remember right now. That's why I posted it. For you. So ask questions, review, homework, whatever. All right. Newton's third law. I need 2 volunteers, pretty please. Sold? And red shirt. Come on down. It used to be my favorite. I'm not sure now, but I like this one. So if one of you would sit here and one of you here, yeah, it's safer. Crisscross applesauce, face each other towards the ends here. Will work better. So we're doing it on rolly carts to try to eliminate friction, not completely. You'll need your feet up so you're free to roll, whatever's comfortable. We'll scoot you together. And we're going to have you put your hands up, touching each other. Sorry, got to touch each other. Now, I want you to pretend like you're a rock, a brick wall, and you're not going to move. You're rigid. I want you to push as hard as you can against him. That was good, proved the point, but I was thinking the same thing. It's a little weak. More oomph, more oomph. There we go. Good, but I told you not to push. Let's do it. You're moving. You didn't push? All right, you're the wall then. See if you can hold still. You push as hard as you can. Good, that worked, but you push this time.
I didn't push.
What do you guys think? Do you think they're pushing? Technically they are, and that's my point. You don't think you are, but that's Newton's third law. All forces come in pairs, or any reaction come in pairs.
Every action has an equal and opposite reaction.
That's another sum of it. For every action, there's an equal but opposite reaction. Same thing. I prefer to say it as they come in pairs, but opposite in direction. Thus, thanks for helping me here. So when you're pushing that way on him, you affect his mass's acceleration, right? Newton's second law. But it comes in pairs. If you push on him, he can't help but push back on you. Thus, his force on you affects his mass and causes him to accelerate. The force between them, though, is equal in magnitude, opposite in direction. Force is a vector, so it has direction. Okay, good. Let's stay there. You can put your arms down, though. Let's try, what if you're not touching? This time, what if you're pulling? Grab that in. You grab that in. Sorry. All right, this time, you just hold still, and you pull. Whoa, they both moved. So he exerted a force on the pole. The pole translated over here and pulled on him. But the reverse happened also, and they both moved. And did you see how their accelerations compared? Let's do it again. We'll have fun. You hold still this time. You pull. They both move. And this is crude, but about the same. So what can we deduce from the mass of the system here versus the mass of the system here? Yeah, they're about the same because we're seeing about the same acceleration. What if he was really tiny? Who would move more? Yeah, he would, because there's less mass, less inertia. All right, also, we're going to do it one more time. I'm going to have you both pull slowly. See where they start? Let's see where they end. Okay, go. In the middle. Because they were moving the same. If he was lighter, where would they meet? More this way, or still in the middle? You know this. See, you seem confused now. Back up. If he was tiny, his acceleration would be... I'll give you another chance. If his mass was less, tiny, his acceleration would be less. Now you got me doing more. Because he has less resistance, it'd be affected more, greater acceleration. Thus, he's going to move more, right? So I would expect instead of meeting in the middle, they'd meet more on this side because he moved more than he did. Does that make sense? All right, let's do it one more way. If you guys will still humor me. Go ahead.
So, computer has more mass, that means he has more inertia. So that means there's going to be less acceleration, right? Because there's more resistance to change?
More mass does mean less acceleration, yes. I could have said it wrong, but I was saying he had less mass.
Inertia, right? That has to do with the principle of inertia?
Mass and inertia are directly related, yes. This is a medicine ball. You feel it before you surprise each other. All right, now, I want you to chuck it back and forth as fast as you can. Go. Yeah. Good. Not only does it work when you're pushing on each other, but when he pushes on the ball, what's the reaction force? He pushes on the ball. What's the reaction force? They come in pairs. The ball pushes on him. Yeah, it's not him catching it. If he pushes on the ball pushes back on him. Same force, opposite directions. But then that ball comes over here and he has to stop it. So the ball exerts a force on him. The reaction? He exerts a force on the ball. That's what slows the ball down. Same force. But then that causes him to move. The ball pushed on him, so he started moving. He pushed on the ball. That didn't make him move, but the ball pushing back on him made him move, right? So recoil. If you've ever shot a gun, this exerts a force on the bullet. The bullet pushes back on the gun. Cannon. How come the cannon doesn't move as much? It has a greater mass. You guys are free to go. Thank you very much. Hopefully this visual will help you remember this. Yeah, a cannon and a cannonball. A cannonball has a lot less mass than the cannon. So the cannon has a smaller change of motion, acceleration. It's the same force, though. This is the easiest, I think, law of Newton's to understand in your mind, but it seems to confuse more people. So I have lots of examples of this same thing, but that's all this chapter is. Okay, I push on the wall. What's the reaction force? The what? My force on the wall back on, me. How do the forces compare? Equal but opposite. What if I push on him? You'll let me? There, I moved his knee. All right. I pushed on his knee. What's the reaction? It's that easy, yeah. His knee back on me. How do the two forces compare? Newton's third law says they're equal and opposite, and that's where it's confusing. Why did you get confused, though? Say it. Because his knee moved. And that's exactly why I want to bring it up. Why does it not move? Okay, I push on his knee pushes back. You have to keep straight who's pushing on what. If you want to know the motion of an object, you must consider all forces acting on that object, not a different object. So if we want to know how his knee is going to move, it has to do with the force acting on the knee. That was me pushing. The fact that the knee pushed back on me affects my motion, not the knee's motion. And this is can get even more confusing. I can hit this medicine ball whoosh, with a given force. I have no idea what it is. Let's say it's 10 newtons. Whoosh. All right, now I'm going to hit with 10 newtons of force. I'm going to try to swing the same. The coffee filter. Makes me feel better. Okay. How do the forces compare between me and the ball? Equal and opposite. Newton's third law. 10 newtons of force on the ball, thus 10 newtons back on me. Its force on me affected the motion of my fist, but the force that affected this, it was the force on it only. Okay, what force did I exert on the coffee filter? The same? You sure? Sorry. Still think it's 10 newtons? Good, because it is. I came in the same. I exerted 10 newtons on the coffee filter. So, how much force did the coffee filter exert on me? 10 newtons. But this was affected more. Less. Because it has more mass. It can push back with 10 newtons. Well, more so than this can. This can't push back on me. So, in reality, good, you got the pair thing right. I'm really right-handed, so it feels weird. In reality, I want you to know that this force pair is the same. This force pair is the same. But, big but, I did not hit this with 10 newtons of force. This pair's magnitude was less than 10 newtons. But they were still the same. And the reason is because this can't push back with 10 newtons of force. So I can only push on it what it can push back. So for argument's sake, let's say it's 2 newtons. Even though I came in the same. It's still 2 newtons on it, 2 newtons on me. Equal and opposite, Newton's third law. But in that case, it really is less than when I hit this. Because that can't push back. So why didn't the wall move? Because it can push back with the same I'm pushing. It wins. I can't push its mass enough to affect it. Your knee, I could, the way you're sitting. And he wasn't flexing. Good. This is my favorite example. Let's see, they weighed me yesterday, 177 pounds. I won't be too embarrassed. So you stand on a scale, and the scale reads 177 pounds. That's a support force, the normal force. We got my weight down, it's balanced, I'm not moving. What's the reaction? What's the pair? My weight and it's not the force of the scale. It's the weight of the what?
The same force from the scale.
The same force from the what? I just didn't catch it. From the ground. You want to add?
Well, force of the ground, whatever the table.
Because I'm pushing the table, or the scale, it's pushing the table, it's pushing the ground. Still, I'll help you out. What's exerting a force on me downward? From, due to? What causes that? The mass of the earth. Does that help you figure out the pair? The Earth attracts my mass. So the reaction is I attract the Earth's mass. That's the pair.
The Earth is pushing on you.
Yeah.
177 pounds.
So the Earth pulls on me with 177 pounds. But next time you're feeling wimpy, think of your weight and realize you're pulling on the Earth with that much force. I am pulling the Earth up with 177 pounds of force. Well, now I am. In free fall. So, yeah. But again, do we see the Earth move up to meet me? No, because it's huge, yeah. And it has a lot more inertia. Technically, it is moving, that much. But we don't notice it. We don't see it. Because I'm puny. Another key here is when you're doing action-reaction pairs for Newton's third law, they're always on opposite bodies. The Earth's attracting me, I'm attracting it. You see how the force is on opposite bodies? Thus, if you think the reaction to the Earth's pulling me down, force on me, the reaction can't be any other force acting on me, such as the scale supporting me. Action-reaction pairs have to be on opposite bodies. Does that make sense? That means somebody wants to visit me in the back. I hear a doorbell. They'll have to wait. What do I want to... I want to do this one. Okay. Make this the last one. Free up. Here's a scale. Reads force, 0. This is 1 kilogram. Mass or weight? Mass. Very good. So what's its weight? How do we find weight? It's mass times acceleration due to gravity, which is 9.8. So 1 kilogram times 9.8 meters per second squared. Yeah, 9.8 newtons. Let's see. Let's weigh it. Close enough. I can't hold still, see? But there we go. So that means, the Earth is attracting it down. The scale is holding it up. Both of those forces are on the mass, so it doesn't move. So this is a Newton, or 10 newtons, rounding. So I'm going to put it over here. This side's tied off. What do you think it'll read? The scale. Ah. Put it back on the pulley, and is it? Good. Yeah, see, that one likes 9.8 better. Rounding error, whatever. So, quiz time. Not with your clicker. What if I undo this and hang another mass on the other side? Another 10 newtons. What will the scale read? Who thinks 0? Who thinks 10 newtons? Who thinks 20 newtons? Okay, experiment time. Drum roll. Now, I hope this won't be too confusing. This was pulling on it with 10 newtons of force this way. I think you see that, correct? Well, what if it wasn't being held here? Or I didn't hold it up here? What would happen to the scale? If the mass is pulling down and I'm not holding it back up, this thing would just go down. Whoosh. If this was pulling on this side and nothing was over here, it would just go whoosh. So there's another 10 Newton force over here. This is pulling with 10 newtons that way to balance it this way. Thus we see equilibrium. That's how scales work. This reads what force is being pulled on. Think of, say you just made the scale disappear and connected the string. The tension in the string would be 10 newtons. That's how scales work. So, in reality, when you have a tuck... Hi. Got caught on the gas lever back there, the cord, sorry. So in reality, when you're having a tug-of-war, if you're pulling and I'm pulling with 10 newtons, you're pulling with 10 newtons, the tension is 10 newtons. If you're trying to pull a car out of a ditch, and you hook it up and you pull, you'd be better off putting, what do I want to say? So you pull something apart, we'll keep it that way. You're trying to rip something in the middle. We could pull this way and we can get 10 newtons. You're better off if we tied it off to one side and then I came over here and helped him out. Because he can pull with 10 and I can pull with 10. Now we can pull with 20 this way, can't we? What's the tension going to be over here tied off to the wall? 20. Newton's third law. So the tension in the rope will now be 20 newtons. And you can get more force in the middle there doing it that way than you can being on opposite sides. Think about that. There's examples in your book. We'll continue this more Friday.